When you buy a robot like this TurtleBot off the shelf, you can just download a few ROS packages and get it moving right away. But when you build your own robot, like this one from my last video, the code doesn't exist yet. So how do you get new hardware connected and driving with ROS? Well, that's what I'm going to show you today using ROS control. ROS control is a set of ROS packages that includes library code and command line utilities to help us expose the controllable joints of our robots to ROS. Here's the pipeline I'm going to be setting up today. On this end, we've got the actual hardware, so power going out to motors and speed readings coming back from encoders. And on this end, I've got the commanded body velocities for my robot, a linear component for how fast the robot is moving forward and back, and an angular component for how fast the robot is turning. So to connect the commanded body velocities from our high-level code down to the actual hardware, I'm going to break this pipeline into 3 stages. The first stage closest to the hardware is the Arduino. This is the microcontroller that's actually mounted on the robot, and it's running firmware that includes PID controllers. These controllers keep our motors running at a specific commanded speed so that everything upstream of the Arduino can just be dealing with wheel speeds instead of the specifics of how our hardware operates. The next stage is the hardware interface, and this is a bit of custom C++ code that's actually running on the laptop, and it has 3 jobs. It needs to manage the USB connection to talk to the Arduino and thus the rest of our hardware. It needs to host ROS controllers that can actually control the robot, and it needs to manage the ROS joints that will represent our wheels. When it comes to these joints, we're going to have one for each wheel, and the hardware interface code is going to create joint handles that are exposed through ROS control interfaces, so that the rest of our ROS code knows about our wheels. Once our handles and interfaces are set up, the rest of our hardware interface code can interact with these joints through the state and command variables in our class. Hosting ROS controllers is done through the controller manager, a utility that hosts its own ROS interfaces for loading and unloading controllers. The flow of the hardware interface code is managed by the update function. This update function gets called repeatedly, and it has 3 steps: read, update, write. Our read step takes information from our hardware and updates our joint states accordingly. This is also the step where any other information coming from our robot could get published, like this battery information. The update step provides an opportunity for all of the controllers that are loaded in the controller manager to respond to the new state coming from the robot. Some of these controllers will use that information to generate new commands for our joints. The write step takes the latest commands from our controllers and sends it down to the hardware to execute those commands. With the hardware interface done, ROS can now control and monitor the speeds of our left and right wheels. This takes us to our last stage, the diff drive controller. The diff drive controller is a controller that comes with ROS control and is responsible for doing the kinematics math that converts these commanded body velocities into left and right wheel speeds, and takes the left and right wheel speeds we're measuring from the robot and converts those into odometry messages. We don't have to write any code for this controller, we just need to set up a config file. This config file might be long, but you can copy most of it from the ROS control documentation. There are 2 parameters that are the most important in this file. Wheel separation is the center-to-center distance between our wheels, and wheel radius is the radius of an individual wheel. The rest of these parameters are mostly related to how odometry messages are published, and any limits that we want to apply to our commanded body velocities. And that's my whole pipeline. I can now set up a launch file that will load my config files, run my hardware interface node, and spawn the controllers that I want to use. In my bring-up package, I've also defined a launch file that runs the joystick node and a teleop node that converts joystick messages into command velocities. With these 2 launch files running, I can now use a wireless gaming controller to drive my robot. By breaking this problem down into multiple stages, we've kept the individual bits of code pretty simple. That said, I know I glossed over some of the specific details, so you can see the full code I set up at the GitHub repository for this project. Now I've got a robot that can move around, so the next step for the RoboMagellan competition will be localization, or how the robot keeps track of where it is.